So today I will talk about the Trappist-1 system. So as we heard before, it's a system of 7 rocky planets around another star, so around the star called Trappist-1. And it basically has one for every taste. So Trappist-1 is one star in the Milky Way, and the system was observed using the transit method. Transit, for those who have it. And those who were last time here, they heard it already about the transit method, but I will explain it again. So it's about those lucky occasions where we observe a star and the planet passes in front of it in our line of sight. So it would look something like this. If Jupiter would be transiting the Sun, so if we were on somewhere else and would observe the Sun from very far away, then we would observe something like this dip here. So we continuously measure the brightness of the star, and then we would see a decrease of 1%. But if we want to observe something like the Earth in front of our Sun, it would look like this. So it's very tiny, and this is actually magnified by 10 times, so it's only 0.001% of the brightness of the Sun. But what if we observe a smaller star? Then we basically get a larger signal again of 1%, just because of the fact that the star is smaller. And there's another benefit if we go to smaller stars to observe with the transit method. It's because the habitable zone, so it's always a little bit difficult to speak of habitable, but we agreed basically everybody agrees that it's about liquid water on the surface. So the habitable zone, when we call it like that, we actually just mean that if it has water, it could be potentially liquid on the surface of the planet. And this habitable zone, which is quite far away, so about at the location of the orbital period of 1 year, as we have it here, so quite far away of the star, would move closer to the star if the star is lighter. So you move to, and cooler by that. So you move to closer orbits, and then you have a transit more often. So it's the interesting zone that everybody is interested is closer, so you get more transits of those stars. So that's why it's nice to go to look at small stars. And Trappist is such a small star, it only has 10% of the mass of our Sun, and it's only the size of Jupiter, so it's very tiny for stars. So it's actually on the lower limit of where you are still a star, because you can still burn hydrogen. And used was the Trappist telescope, which is in Chile, and it's also a beer. So cheers, those who have one. And the Trappist beer is named after the monks who brewed the beer in Belgium, and this telescope is in honor of those monks. It's also called Trappist because it's a Belgian telescope. But it is not in Belgium, it is in Chile. And why? Because the nights look so beautiful there. So I wasn't there yet, so certainly go. But to observe the 7 planets, to find all those 7 planets, was not just the ground-based telescope, but it was also a space-based telescope that was used, which is this one, the Spitzer Space Telescope, built by the US. And what did they get? So this was last year, and they used it, and they got a very nice signal. So this is what the system looks like. So it has those 7 planets, and the orbits are to scale, so it's all very compact. And you also see some resonances. Okay, it will not run long enough. So here we get the actual data. So this is all these points. Every point is a measurement of the Spitze space of the telescope, and you can see that there are those dips here. And each time a planet passes in front of it, it will make this dip. You can also see a flare here. So the star is not always the same brightness. It has outbursts and flares. And these are those. You also measure them. But they found very regular. So this is actually for astronomers a very good spectrum, very good light curve to see all those transits so clearly. And they got a single transit only of the planet H. It already passed. It's the outermost one, but because the data is so good, they could guess quite clearly that it is actually a planet, because each signal is so clear. And it was later also confirmed that planet H actually exists, and they determined the period better. And some guys also put it into some music. So the Trappist system makes music. We have one note each time in the transit, so the transit would be from the right. And the faster the orbital period, the higher the pitch, the note. So we add them all together here. So now you listen to space music. And we get one more. And now we need some drums. So we have a drum beat each time they pass each other. And you can also see that the second outermost one makes 3 orbits in the time the outermost one makes 2. It's the resonances that we have. A huge mess. So it also makes nice music. That's how it looks like in terms of sizes. This is the whole Trappist system. If we would put it into our solar system, so Earth is here, and it's so tiny it all fits into the orbit of Mercury easily. So it's actually not much bigger than the orbits of the Jupiter moons or the Galilean moons. It's also quite similar in size. And it fits all those 7 planets. It's quite astonishing that they don't crash. And because it's so small in size, the tides are stronger because it's closer to its host star, and which makes the rotations, if they had a rotation around their own axis, slow down such that they always face to the sun with the same size. Well, that's a theory, of course, but it's quite sure that this will happen. And it's like our moon always faces with the same side towards Earth because of the tides. And then, assuming that, we can of course make nice movies again of how they could look like. So this would be planet B. It's the closest one, it's the hottest one, and then if we move further out it gets less hot. And planet C, which we will see next, could already have ice on the cold side of the constant days. Maybe it looks like that, but maybe it could also look like that. So here you have some Trappist beer now, finally. So, but what we know is is this. No nice pictures, but this one. But this is, for us, it's fascinating enough because you have very good, for astronomers, very good data. So you can see all those digits after the comma in the semi-major axis. And what I like, especially, is the masses. You usually don't get masses with the transit method. You have to infer them from tiny variations in the orbit. You have to calculate all the influence of the other planets by gravity to get the masses out. So this was done in Bern this year. So these masses are now the updated Grimm et al. For the experts. So Simon Grimm did these calculations here. And we, of the theoreticians who care about planet formation, we like, of course, the masses, and we like to know how to get to those masses and to a system like that. And for that we have a model of planet formation. So what we know about planet formation is that there are nebula that are observed, and these are giant star-forming regions in the. So they contain a lot of stars, and in those nebulas you might have a denser cloud that collapses to form a new star. And when this happens, so this is no longer data, this is now computer animation. First picture was data. You might form a star at some point, and because the cloud had some angular momentum, when the gas comes close to the star, it speeds up like an ice skater, and then you form those disks around the stars. And in those disks, so they are observed as well, the planets have to form in some way, and it's all masked by the gas and the dust in there, so we don't know in all details what happens, but we have computer models and we can test different kind of models. So then you would collapse into the planets, and they sweep up a lot of dust and whatever solids are in there, and also gas. And then the disk gradually gets thinner, and in the end it's gone after some 3 to 10 million years. And in the end you might end up with something like our solar system, or with a system like Trappist. So ideally, your model would explain a solar system-like system or a Trappist-like system. Thanks to Mark for this nice movie. And so just to sum up, in our planet formation model we assume that it's the core accretion model. So you have some cores that accrete all the gas and dust onto them, so just by gravity all the other solids and gas get onto these cores. And then we make a lot of statistics, so we run the model many times, and then we compare what we get out of the models with the actual data. And I do such a comparison shortly now. This works. What it looks like. So I put the Trappist planets here, and the white ones are the formed, so these are the theoretical planets that we managed to get, and the colored ones are the Trappist planets. So you can see we formed one here and one very close here, and I of course like to visualize it like that. But when you use it, there's quite dry statistics. That's what we do. So with that, I show you the Google landing page who honored the Trappist-1 discovery, and thanks for your attention.